In this screencast, we are going to look at the work done by moving electrical charges in electric fields. This will change the potential energy. We're going to introduce a new concept. The change in potential energy per unit charge is something that is called voltage. Now, in this chapter, the book itself refers to electric potential. It's a little bit confusing to talk about electric potential and potential energy. So in all of our worksheets, we are going to refer to voltage as the amount of work as a change in potential energy per unit of charge. Now, if we remember with gravitational potential energy, if you take an object, if you take a ball and lift it up, you can increase its gravitational potential energy. You see in figure 7 here, you can observe how this would work. The force of gravity is acting downward on this ball. If we lift it, we're going to increase the gravitational potential energy of the ball. In a similar way, if we have two charges that are attracted to each other, here we have a large negative charge, a small positive charge above it. The electric field is pointed toward that negative charge. If you take the positive charge and separate it, pull it apart, we're going to increase the potential energy, the electrical potential energy of this system. Now there is something, we will again call this voltage. This what the book is calling the electric potential difference is what we are going to call voltage. What this is this is the amount of potential energy per unit of charge. The equation shown here, we see this delta V, this is the change in voltage. Change in voltage is the work on a charge, the energy in a charge per unit of charge. So if you have a battery, if you have something like here in this picture, we see a 1.5 volt battery, what that says is that if we were to pull a coulomb of charge out of this battery, we would get 1.5 joules worth of work out of it. So electric potential voltage is measured in joules per coulomb. So 1 joule per coulomb is also known as 1 volt. So this is a new unit, a new quantity, a new thing that we'll have in these equations. So this figure 8, this will help you in answering questions on the launch homework. We're going to look at differences in potential energy. We're going to look at differences in voltage, see how all these things work together. In this figure, you can see that we have a negative charge. If we have a positive charge near it and we apply a force to it to pull it apart, pull it away from that negative charge, we've done work on the charge. By doing that, we've increased the potential energy. So you can see the increase in the potential energy of the system here. It's the potential energy you began with, add the work done on the charge by you, by pulling that charge apart. Now, on the other hand, you can begin with a charge that is some distance away from the negative charge. If it comes closer, now we have negative work done. This charge naturally is attracted to the negative charge. It wants to get closer. If we do that, there's going to be negative work. And now there's a drop in the potential energy. You see, we have reduced the potential energy by bringing it closer. If we have two charges that are the same, if the two charges have the same charge, then they have a repulsive force in between them. If we were to move them away from each other, then then that would be doing negative work. The energy would go down. We'd have a drop in the voltage. So look at figure 9 here. We can see a few different systems. So here we have two opposite charges, a positive and a negative charge. If we pull them apart, the voltage will increase. If we take two like charges, if we pull them apart, then the voltage is going to decrease. if we have two charges that are the same and we bring them apart from each other, then the voltage is going to decrease. The way to keep this, keep track of all these things is just think of what is the forces acting on these charges, what is the way that they would naturally want to move. Just like with gravity, if you naturally let something fall, it's going to lose potential energy. If you push against the force of gravity, you're going to increase the potential energy. So in all of these cases, if you take two charges and push them against the electrical force acting between them, you're going to increase the potential energy. If you relax them, let them move in the direction that the electrical force would naturally want them to go, you're going to decrease the potential energy. So if we have a uniform electric field, and say we have two large parallel metal plates with positive charge on one plate, negative charge on the other, in between them we would have a constant electric field. So work is going to be equal to force times distance, just same as we learned in the energy unit. So work per charge, the voltage per charge, is going to be the force times the distance divided by the amount of charge that was doing the work. Now, this voltage is going to be equal to the force divided by the charge times the distance. Oh, but that electric field is the force divided by the charge. Therefore, we can say that the voltage difference itself is just going to be equal to the electric field times the distance between the plates. If you push a charge in a uniform electric field, you're going to change its voltage. If you push it in the direction it naturally wants to move, the voltage is going to drop. So if you took a positive charge and pushed it toward a negative plate, it would lose voltage. If you push it toward the positive plate, push against the force from the electric field, then you would increase the voltage. So one last thing we want to talk about is that remember that in a conductor, electrons are free to move. Therefore, what will happen is that if you have a conducting sphere, the charges are going to want to move as far apart from each other as possible. So in this figure, you can see that on the outside of a conducting sphere, the charge is going to be evenly distributed all the way around the surface of the sphere. There won't be any charge on the inside because that electric field would make the charges move. If we had a hollow sphere, you can see all the charges are out on the outside. There is no electric field on the inside. If we have an irregular shape, the charge is going to be more concentrated in areas where there are sharp points. So this tells you, if you happen to be in a thunderstorm, if you were in a car, the safest place to be would be on the inside of the car. If it happened to be struck by lightning, all of that charge is going to go around the outside. It's going to stay out in the metal shell. There's going to be no electric field on the inside. All right, so with this information, you should be able to answer all the questions for the launch homework. Remember that anything in the book that's talking about electric potential, we're going to use the term voltage to make things simpler.